Welcome back to part 4 of our video on the substitution rule, or U substitution. So let's talk about symmetry. In a previous math class, you might have been introduced to the idea of even and odd functions. Let's define what an even function is. So if a function f satisfies the property that f of negative x is equal to f of positive x for every x in its domain, then we say that f is an even function. The graph of an even function is symmetric with respect to the y-axis. So down below, on the left, we have an example of a function that's graphed that is even. And we know that it's even because if I folded this down the line of where the y-axis is, and I fold it over, it has the same image. So why do we care about if a function is even when we are calculating a definite integral? Well, if I have a definite integral of an even function and I'm evaluating the area underneath the curve from some lower limit of integration to some positive integration, if the lower limit is equal to negative a, where a can just be any value or any constant, and the upper limit of integration is positive a, notice that if I took this area it might make our life easier if we folded that in half and just calculated the area using the limits of integration starting at x equals 0 and the upper limit of integration at x equals a. So what I could do is I could instead find this area starting at x equals 0 and ending at x equals a, and then I would just need to double that. So why would we go about doing that? Well, a lot of times when one of our limits of integration is 0, if we're using part 2 of the fundamental theorem of calculus, oftentimes it's easier to evaluate a function at 0. So what we want to say is if we have a definite integral from negative a to positive a of f of x dx, if f is an even function, then this is equivalent to 2 times the definite integral from 0 to a of f of x times dx. And again, this is only true if f is even. But if f is even, this is a helpful equality or equation, so it makes our calculations a bit easier. Okay, let's define what an odd function is now. So if a function f satisfies the characteristic that f of negative x is equal to negative f of x for every x in its domain, then f is an odd function. The graph of an odd function is symmetric with respect to the origin. Now, another way of saying that, if you look at the graph of a function, you can tell that it's odd if you rotate the graph 180 degrees, either clockwise or counterclockwise, and you end up with the same graph. So down here on the right-hand side, we have the graph of an odd function. And why do we care about the definite integral of an odd function if the limits of integration are from negative a to positive a? Well, what's going to happen is these are going to be the same area, except one's going to be above the x-axis and one is going to be below the x-axis. And previously we learned that a definite integral essentially tells us the net area, and so we're thinking about it as a net area. So we can think about this area above the x-axis as being the positive stuff, and the area below the x-axis is what we're subtracting off. And if they ultimately have the same area, then if we have the definite integral from negative a to positive a of f of x dx, this is going to equal 0. And again, this is only true if the limits of integration are from negative a to positive a. So something like negative 4 to positive 4, or negative e to positive e, and f only if f is an odd function, because it has this special characteristic. So let's see if we can't put these properties to good use. Example 8 says, evaluate the following integrals using symmetry. So in order to use symmetry, we have to check the limits of integration. So let's do that. In part A, my lower limit of integration is negative pi over 3, and my upper limit of integration is positive pi over 3. So in terms of our limits of integration, we're good to go. But we have to also check out our function. And in order to use symmetry, we need to check whether our function is odd or even, or neither of those. And if it's neither, then we cannot use symmetry. But our directions specifically say to use symmetry, so our function is probably going to be either even or odd. So in order to proceed, you might have to recall an identity from trigonometry, and that identity tells us that sine of negative x is equal to negative sine of x. And we know that sine is an odd function, and if you don't remember that, you can also think about what the graph of sine looks like. So if I were to graph sine from, say, negative pi to positive pi, here's 1, here's negative 1. The graph of sine from negative pi to positive pi looks something like that. And if I rotated that 180 degrees, either counterclockwise or clockwise, it would return the same graph. So sine is an odd function, but that's not what our integrand is. And so the integrand f of x, or that function there, is equal to x to the 4th times sine of x. And so the way that we're going to check what characteristic this function has is I'm going to take my function and I'm going to plug in negative x. So let's see what happens. I have negative x to the 4th power times sine of negative x. And that is equal to, if I raise negative x to the 4th power, that is going to simplify to be x to the 4th power. And then I'm multiplying that by, and we said earlier that sine of negative x is equal to negative sine of x. And so the negative 1, I could pull that out to the front. So I have negative x to the 4th power times sine of x. And this is exactly equal to negative 1 times the original function, or in other words, negative f of x. And so because we have f of negative x is eventually equal to negative f of x, this shows that, so I'm going to write, this implies that f is odd. So because the function that we're integrating is odd, and because our limits of integration satisfy that property that we're looking for, we can conclude that the definite integral from negative pi over 3 to positive pi over 3 of x to the 4th times sine of x dx, we know that that is equal to 0. Okay, so we're back with part B, and we're going to check our limits of integration. So our upper limit is 1, and our lower limit is negative 1. So it satisfies the property in terms of our limits of integration. And I'm going to call f of x, this function here. So f of x is equal to x to the 8th plus x squared. So if f of x is equal to x to the 8th plus x squared, I want to come and evaluate f of negative x and see what happens there. So if I plug in negative x, I have that plus negative x squared. And because both terms are power functions and our powers are even, negative x to the 8th power ends up simplifying to x to the 8th power plus, and then negative x squared ends up being x squared. And notice that that is our original function. So that is equal to f of x. So to reiterate, because f of negative x is equal to f of x in this case, this implies that f is an even function. So what that means is, to make my life easier, I can take my original integral and this is equal to 2 times the definite integral from starting at 0 and ending at 1 of that same integrand. And again, we still have to integrate, but because our lower limit is now 0, it should make our final calculation a little bit easier. So let's take the antiderivative of x to the 8th. That's going to be x to the 9th over 9 plus, and then for x squared, I want to increase the power by 1 and then divide by that new power. So don't forget your brackets or parentheses. And we're evaluating this thing from x equals 0 to x equals 1. And then also don't forget that 2 out front. So now our upper limit of integration is 1. So I have 1 to the 9th power over 9 plus 1 to the 3rd power over 3 minus, and then what's nice is if I evaluated that antiderivative at 0, 0 to the 9th is 0, divided by 9 is still 0. So that entire thing is just going to end up simplifying to be 0. So I have 2 times 1/9 plus 1/3. And if I find a common denominator and multiply, this ends up giving me 8/9 as my final answer. And that concludes this example.